Good. All right. So relative speed, here's what this means. Very easy to understand. You have a wave and you have a wave. Let's say, Aisha, that your wave is traveling at a rate of 90 meters per second to the right. Zavari, let's say that your wave is traveling at a rate of 120 meters per second to left. Let's say that, Aisha, you know your starting location. Zavari, you know your starting location. If you haven't done so already, you can use Google to find out the distance they are apart. And that number I would like to be in meters. And let's say that that turns out to be 300,000 meters for you. Here's what I want to do. What I really would like to happen is I would like to first calculate how long it takes until they hit each other. I then want to calculate how far each separate wave has traveled to get to that point. And then the last piece is understanding what the wave looks like at that point. So time, distance, and then understanding what the graph looks like at that location.
You said the time for to hit each other.
Time for the waves to meet, the distance for each wave until they meet, and what the wave looks like when they meet. The real goal is to find what they look like, because just like the superposition workshop you all did with Coach T yesterday or the day before, you physically know what the waves look like, and then you can just quickly figure out what happens when they meet. So this whole thing is just to figure out what part of your graph you're going to have when they meet each other. So here's what we're going to do. Relative speed. I really would like to use this equation, distance equals rate times time, to calculate the time it takes for the waves to meet. But the problem is that I'm not talking about one wave, I'm talking about two waves, and one's not stationary, they're both moving towards each other. So let's think about this. If I am moving towards Zavari at 5 meters per second, and he's stationary, to him, how fast do I appear to be moving? 5 meters per second. Because he's stationary, I'm moving. Now let's say we're gladiators. Zavari's running at me, I'm running at Zavari. I'm going 5 meters per second, he's going 2 meters per second. How fast are we going relative to each other? 7 meters. 7. Add the two speeds together. So for these waves here, to find their relative speed, which is the same thing as rate, which is the same thing as velocity, what do I have to do with these two numbers? Add them. So what would my relative speed be for these two waves? 210 meters per second. Now remember, you each should have calculated the velocity of your waves using that equation, rad equal g times d. We did that way back when, I think it was last week sometime. If you haven't done it already, it's an easy calculation to do. Okay, so I can now use this equation, distance equals rate times time. The distance the waves are traveling is what? 300,000. So I use 300,000 for my distance. What is the rate at which they are traveling with respect to each other? 210. And I want to solve for the time it takes for them to meet. So notice this actually changes to a relatively easy problem here. I divide both sides by 210, and I get that my time is 1,428.57 seconds. So again, we did distance equals rate times time. Our distance was 300,000. Our rate was 210. Divide both sides by 210 to get a time of 1,428.57 seconds. Great. So that's the first step. What was the second step? I need to know how far each wave traveled. So if you think about this, if the distance between the two is 300,000, what's the halfway point?
15.
Yeah, like 150,000. And if this wave is traveling faster than that wave, are they going to meet right at this line? Are they going to meet to the left of this line or to the right of that line?
Yeah.
To the left. To the left, somewhere here. The problem is I need to know exactly where. Because if this wave comes in like that, the superposition of the waves is going to look very different than if the wave is coming in like that, which is going to look very different than if the wave is coming in like that. So do we see why it matters what the wave looks like? Cool. So I need a distance to figure that out. So here's what I'm going to do. We're going to use distance equals rate times time again, but now we're going to use it for each individual wave. Let's say I use it for this wave right here, Aisha's wave. Well, I'm going to do distance equals rate times time. The distance is what I'm trying to find, so I have a d. What is the rate of this wave?
90 meters per second.
90 meters per second. What's the time it takes to meet? The number I solved for, which is why I need to do that first.
You use the same time for both of them?
Yeah, because that's the time it takes them to meet.
Okay.
And if I calculate this, I get a value of 128,571.3 meters. Cheers. Notice, the distance between the two cities, I do not have in miles, I do not have in kilometers, I have in meters, because every one of my speeds is in meters per second. I want my units to match. Great, so this is the distance this wave travels. Now here's how I'm going to use this piece of information connecting to the benchmark you already completed for me. Let's switch this over a little bit. Okay. For your benchmark, you had to find an equation. You also had to graph that equation. So I know what my wave looks like at every single meter that it travels. Now, what I really want to do is I want to see what my wave looks like for this distance. So what I'm going to do here is I'm going to look at my graph and notice, since my wavelength for this wave was 100,000, I stopped at about 96,000 because, of course, I shifted everything left a little bit as my phase shift. I would really like to know what it looks like at 128-something thousand. So in my graph, what do I first have to do? I have to continue the wave. So remember when we developed our equation, we took our wavelength, we divided by 4, and we got how far apart each section of the wave is? All I'm doing now is I'm just continuously adding that until I get to the number that I would like. So I have 96,000, I add it, I get 121,240, add it again, I get 146,240. Why do I stop at the 146,240?
It's greater than 128.
It's greater than 128. So I go up to a max, I go back to an x-intercept, I continue my wave. Now on my equation, where is 128 something 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 located? About. Just past my 121 mark. So I know that my wave is going to collide right there. The last piece of this is I need to know exactly how high the wave is at that point. So I have an x value, a distance. I have an equation that tells me how high the wave is. What do I do with those two? I plug that distance into this equation and it tells me how high my wave is.
What if you just use the amplitude to just see how high it is, like 10?
So that's going to give me a good guesstimate. I know it's just below 10. I need to know exactly how much though, because with your workshop with Coach C, you need to know the exact number of the amplitude. So I plug this distance into my equation and I can get the coordinate points right here.
Where do you plug it at?
To your equation you have for my x value. Yep. So I'm going to put an arrow to x and distance goes here. If you do it right, it should be a number that is in between the top part of your wave, 10, if you chose 10 for an amplitude, and the bottom part of your wave, -10. Cool. So, steps. First, relative speed. Add your wave speeds together. Second, use distance equals rate times time to find out how long it takes the waves to meet. Third, use distance equals rate times time to find the distance each separate wave has traveled. Next, you individually are going to continue your graph so you know what the wave looks like. And then lastly, you're going to plug in your distance to the equation that you individually have to find the height of your wave at that point. If you have a picture like this, then you are ready to attend Coach C's workshop and figure out what happens. For the sake of time, you might want to attend Coach C's workshop first and then just do it all at once, either today in class or over the weekend. So you're good for Monday. Make sense? Any questions?
So if you plug distance into that, what are you solving for?
I'm not solving for anything. I'm multiplying everything out.
Okay.
Yep. So I should get a value of like 9 something probably, or 8 something. We good? Cool. The only problem point that might happen is, let's say you get a distance, it's like 3 million something. I really don't want to have to keep adding things 3 million times. If you get a distance like that, just let me know, and if you can't figure out what your wave looks like, I'll give you an easy way to do it. Capiche? Great. And workshop. Fantastic.